Good evening, everyone, and welcome to this week's BAA Wednesday webinar. Just letting you a few bits to begin with. This session is being recorded, as well as being streamed to YouTube, and the recording will be available on YouTube afterwards. And we're going to be doing a Q&A after Hugh's presentation. So if you can keep the questions to the end, and there's a Q&A box you'll be able to go to at the bottom where you can type your questions. And for the Q&A, as well as Hugh Allen, we'll have myself, Andy Wilson, Robin Ledbetter, and David Boyd. It's my pleasure to welcome Hugh to give this webinar on a topic which is something I'm very interested in. Hugh Allen is the chairman of the Wells and Mendip astronomers. His title of his talk's From Kitchens to Comets, Hunting Molecules with a Spectroscope. And I've known Hugh for a good few years because we both have an interest in astronomical spectroscopy. So and Hugh is certainly very talented with his Alpi spectrograph. So what I'll do is I'm going to stop sharing now, Hugh, so you can then take over the reins with your talk.
Sure. Thanks, Andy. Thank you for the kind introduction. I'll just share my presentation. Does that come through okay, Andy?
Yep, I can see that good.
Excellent. Well, look, good evening, everybody, and thanks very much for joining in this webinar about spectroscopy. I have to say, I give a lot of talks about spectroscopy. I'm a bit of an evangelist, but I've never given a webinar before. This is my first webinar, so bear with me. So look, here's an outline of my talk today. I'm going to spend a few minutes giving an introduction for various different reasons. You'll see, I know many people perhaps don't know so much about spectroscopy, and so there'll be a bit about the technique and some of the history, and then we'll get going, and we'll start in the kitchen, and this is where I am this evening, and the idea there is just to kind of introduce you to molecules and how we see them in a spectroscope, so you learn a bit of how to recognize them. And then we're going to look at 3 different areas where we can find molecules with an amateur spectroscope. So planets, which I guess you'd expect, that's where you'd find them. Maybe less so in stars, but they are there to be found. And we'll finish with a few slides about comets and how they link to activities here in the kitchen. And then, yeah, as Andy mentioned, we're going to have a Q&A, and I hope I won't embarrass the panelists who are going to be on the question and answer, but we have 3 of the finest UK amateur spectroscopists on the panel. So please ask lots of questions. There will be loads of expertise. So yeah, a few introductory remarks. First of all, just to introduce myself a bit, Andy said I'm the chairman of Wells and Mendip Astronomers, and there's our logo. I don't know how many of you have visited Wells, but this is where we have many of our meetings, not in the cathedral itself, but in the museum next door. And this is one of the finest Gothic cathedrals in England. In fact, Wells is England's smallest city, being a cathedral city. A beautiful place to visit. We have our meetings of the Wells and Mendip astronomers all over the Mendip Hills. Pretty dark skies we have, and here's a picture of me observing up in Oak Hill, which is actually the village in the Mendips where I live and where I'm broadcasting from tonight. I do have other passions besides astronomy. Badminton is definitely one of them, and there's me serving to my wife, about to smash the shuttle back to her after her return. I have a family. Chrissy and I brought our 2 families together, so lots of children, but fortunately they've all grown up, started careers or at university, so the house is pretty quiet at the moment. And by profession, I'm an industrial chemist since graduating from Downing College in Cambridge with a degree in chemistry. I've been in the printing ink industry for my whole career, working on inks for inkjet printers in the last 10 or 20 years. But look, we're here to talk about spectroscopy, and this actually is the first light image from my Alpi spectroscope, which I bought back in April 2015. So I've been doing astronomical spectroscopy now for a good 5 years, and I have enjoyed every minute of it. And I have to say, I guess I was initially interested through my chemistry connection, but really, and I hope you'll agree by the end of this talk, it's an absolutely fascinating area of amateur astronomy. So look, let me say a few words about the tools of the trade. I have two spectroscopes, actually. I have a star analyzer, and many of you may have heard and even own a star analyzer, because it's often the place where amateurs begin spectroscopy. Very simple piece of kit. It's really just like a thread-on 1¼ inch filter. And indeed, the designer of the star analyzer is one of our panelists for the Q&A, Robin Leadbeater. And this has been on sale now for some years. And there are probably, I think, thousands out there now amongst amateur astronomers. And really, you just thread it onto the nose piece of your astronomical camera, your CCD camera, slot it in the back of your telescope where you normally would for doing astrophotography, and there you are. Your field of view will be full of spectra of all the objects that are visible in the field of view. So it's very simple, very low cost, easy to use, an easy way into spectroscopy. But I knew from the outset I wanted to start with an ALPI, and that was my first spectroscope. Much more complex piece of equipment, but there are rewards for that. And these two photos here, I'm just circling the one of the slit from an ALPI. So this is a spectroscope that contains a very narrow slit to control the light that gets through to the diffraction grating. And you can just about see the slit here in the image, I think, a 23 micron slit in a mirror. And the mirror allows you to use a guiding camera to follow with the guide camera what it is you're observing and how you're placing it on the slit. And this is just a photo of the complete setup. So this white box here contains two lamps, a flat lamp. Astrophotographers will be familiar with taking flat images to calibrate their images. And there's also a calibration lamp in here that produces lines of known wavelengths. So you can calibrate the images of spectra by wavelength. And then the slit goes in the guiding here with the guide camera above. The spectroscope is in here, and the spectroscope, the ALPI spectroscope, has optics which collimate the light onto the diffraction grating to give maximum resolution, and then focus the light onto the imaging camera at the end. But what do you get for having this greater sophistication? Well, I tried to put two spectra here next to each other. So this is the star analyzer spectra, this is the star Vega, and this is the ALPI 600. And you can see, I hope, that with a slit and the optics and the higher resolution grating in the ALPI, what you get is a much sharper, higher contrast spectrum with very fine features visible that you don't see at all in the lower resolution, more apparently blurred spectrum from the star analyzer. So yeah, you get more capability, but of course at higher cost, and because you're spreading the light out much further in an ALPI, you need to take much longer exposures. So most of the spectra you're going to see in my talk are taken with the ALPI. And of course, like any branch of amateur astronomy, there's a learning curve. So you don't just have to take images of the spectra, you then have to process them in specialist software. Here are just a few examples. I started with RSpec, which is quite common with beginners, and I've moved on to BAS. Perhaps the highest capability software which is recognized amongst amateurs is ISIS. And then Dimitra is a new piece of software from Sheliak, who are the builders of the ALPI 600 spectroscope. And I think I should say a few words of thanks to the BAA. I'm a BAA member, and they have really helped me on my journey with my spectroscope. And here we go back 4 years to a whole weekend of spectroscopy organized by the BAA. And you can see some significant people in this photo. So here you have Francois Cochard, who's the owner of Sheliak, and he gave many of the presentations at this course. And then there are the three panelists on our Q&A here. So you have David Boyd. I'm sure they won't mind. I hope they don't feel they look a bit like spacemen. You have Andy Wilson and Robin Leadbeater. So these are the three people who are going to be helping me answer questions at the end. And that was a fantastic weekend, all focused on training in spectroscopy. And I noticed an article in the April BAA journal about some of the new things that BAA are doing to support amateur spectroscopy. So Andy writes about the mentoring scheme, and I've just become a mentor. for new spectroscopists. And Jeremy Shears talks about the spectroscope the BAA has available for loan. And on the right here, this is the BAA spectroscopy database that Andy has built. Now has thousands of spectra preserved for forever, if you like, for scientific use and for other people to consult. And it's a public database, a growing resource. And when I give talks about spectroscopy, I like to talk a little bit about the history of spectroscopy. I feel that's a good way for people to sort of understand the subject. So, of course, the history began under lockdown. Poor old Newton was escaping the plague of 1666, and in his home he had many great ideas, one of which was, of course, the analysis of sunlight and the understanding, the proper understanding of the spectrum that is generated when you pass sunlight through a prism. And of course, we think we're very familiar with the spectrum of the sun. We see it in rainbows as refracted spectrum through raindrops. We see it off the back of CDs and DVDs as a diffracted spectrum. But like Newton, what we fail to see is any of the features in the spectrum. And it's intriguing to think why Newton missed any features in the spectrum. Maybe his opening here that he let the sunlight through was too big. Maybe the quality of the prism, the glass he was using. Maybe the fact that he cast it onto a very distant wall. But he failed to see any features in the spectrum. And I often wonder, if he had seen features, how the history of spectroscopy could have been very different. We had to wait nearly 150 years. Fraunhofer wasn't the first to see lines in the spectrum. That was Wollaston who saw them about 10 years before, but Fraunhofer really was the first to do scientific investigation. He was a glassmaker, and he was using the analysis of the spectrum of sunlight to test the quality of his glass. And he actually observed, and this is a drawing from his original paper, he observed over 500 lines, dark lines in the spectrum of the sun. And this is an absolutely exquisite drawing. And not only that, but he recognized that spectra have shape. So there's a continuum of light in the background, and which is the brightness of the spectrum, which peaks in about the green area of the spectrum. I thought that was a beautiful drawing. And he didn't just think about the spectrum of the sun. He did actually point his spectroscope at the stars. And he did some, albeit brief, work on the spectroscopy of some stars. He wrote this in an obscure paper in the Edinburgh Philosophical Journal, and actually commented on what he saw and hoped that others would sort of take up the baton. But they never did. Again, this is something interesting to think about in the history of spectroscopy. And it was another 50 years or so when we come to the work of Kirchhoff and Bunsen, two very well-known names now. Here's their photo, Kirchhoff on the left and the much taller Bunsen. And of course, Kirchhoff was the physicist, Bunsen the chemist, and together with their spectroscope design, they analyzed the emission spectra, lines from chemical elements in flames, and recognized that these matched the lines that were visible in the sun. And Kirchhoff synthesized all this, and there'd been a lot of spectroscopy before that, of flames and so on, as we'll see in a minute. But it was Kirchhoff who synthesized the physics and basically explained that light from hot bodies like stars, for example, is produced in a continuous spectrum. But if that light passes through a cloud of gas, for example, the atmosphere of a star, and we view the light through that cloud, then these chemical elements leave a fingerprint in that light of absorption lines. But that if you're viewing, if you like, the cloud of gas to the side, then if you like, what goes up must come down, and the cascade of energy back down produces emission lines. And these are identical in position to the absorption lines. They're two sides of the same coin. And just like the absorption lines, they are the fingerprint of chemical elements. And it was as if this explanation, this synthesis, sort of kicked off astronomical spectroscopy, because within a few years, there were several pioneers of astronomical spectroscopy. And here are two that are going to feature in my talk: Angelo Secchi and William Huggins. Angelo Secchi was a Jesuit priest, and like many Jesuits, very highly educated. And he he produced many classifications of stars, as we'll see. And William Huggins, who's my spectroscopic hero, he basically launched astrophysics in terms of spectroscopy, and we'll see many of his contributions as well. And here's Huggins as an old man, and he wrote an essay in 1897 near the end of his life where he looked back on his career. And one of the comments he made was, spectrum analysis could not fail to have a powerful influence on the future of astronomy. And I think it has done in professional astronomy, undoubtedly. You cannot do professional astronomy without spectroscopy. That's how we understand really what's going on at these great distances. Less so perhaps for amateurs. And I put these three kind of aspects of what spectroscopy certainly means to me, and I hope it'll mean to a lot of amateurs. There is beauty in spectra. And honestly, spectroscopy is just a different way of observing the sky. But of course, spectroscopy is a quantitative aspect of amateur astronomy. So you can do absolutely fantastic science and detective work as well. So look, let's get started. So we're going to start here in my kitchen. And we're going to look for molecules in the kitchen and basically learn how to recognize them before we start shooting off into space. And here's the setup I used to take the spectrum of the gas hob flame, that beautiful blue flame that is produced on your gas hob. And this is how the camera sees it. So this is an image straight out of the camera, and you can see all the sorts of artifacts that perhaps astrophotographers are used to seeing. You can see hot pixels here. You can see there's a dust mote on the slit. That's this horizontal line. And here are the emission lines produced by the flame. They have a bit of a shape to them. They have a curve. They have a slight slant. And all of these things is what you use the software to correct for. And you're going to get used to seeing these, I'm afraid, because one of the best ways to then visualize that spectrum is as a graph, an intensity graph. So you plot the relative intensity on the y-axis, and you plot the wavelength on the x-axis. And I've colored these first few so that you get used to the idea, but the way you plot it is short wavelengths to the left and long to the right. So you plot from the near UV here down on the left, right the way up to the near infrared on the right. And what you're looking at is the plotted spectrum of the light emitted by the gas hob flame. And what you can see is that there is actually a continuum. In fact, I'm just going to draw that line on. I'll take it off and draw it again. And you can do this in the software. So there's a continuum of light in the background to the flame, which peaks in the near UV. And then this continuum has sort of compounded or superimposed on it the emission lines that the flame produces as well. So what we're going to do, and this is a technique that spectroscopists often use, we're going to remove the continuum so we can focus on these beautiful emission lines, and you can subtract that continuum in the software. There, by the way, at the bottom, I've just put the visualization of these two spectra. So the top there is the full spectrum with the emission lines, and the bottom there is my estimate of the blue curve of the continuum. So if I remove that continuum there's these beautiful emission lines. There's a particularly intense one here in the blue, and that contributes to the blue color as well as that continuum light. And it's so tall, the relative intensity is so high that what I'm going to do is I'm going to crop the x-axis kind of here as if I'm zooming in. And then you really see these different emission lines. And you can begin to see now which ones are molecules, because if I pick out the atomic emission lines, there's sodium. Many of you, I'm sure, will recognize that as the nice yellow sodium light you get from those annoying street lights. I used to have one of them outside of the house before we went to LED. And then to the right here, you can see the same emission line produced by potassium. This time the doublet is at much lower energy, longer wavelength light, and it's actually split in my spectroscope. You can see how these are very thin and sharp, very contrasting to these molecular lines, which are basically bands. And notice how these bands have a gentle slope on one side, and then they have a kind of cliff edge, what's called the band head. And when spectroscopists talk about the bands from molecules, the band head is often the wavelength they quote, this cliff edge. And you can see these emission lines, these bands, the cliff edge is on the red side, and the band fades away to the blue. And then we can look up the position of these bands, the wavelength in catalogs, and we can identify them. So it is typical in these kind of high energy situations like flames. The molecules we see, they're actually what chemists call free radicals. So they're not stable in normal conditions, but in the energy of a flame, we can detect them. And these emission lines here, these bands, these are the CH radical. And then the other most prominent bands are what's called the Swan bands. And these are produced by diatomic carbon. And just for the chemists, I've put the chemical structure here of the molecule of diatomic carbon. And they're called the Swan bands because they were first observed by William Swan in the mid-1850s, who studied flame spectra with a prism. And he studied these and saw these bands for the first time, and they now carry his name. I think these are absolutely beautiful. There's one other band that I want to point out, water, which of course you get in a flame because some of the hydrogen in the hydrocarbon burns to form water. Notice it's not very strong, but notice how it actually fades in the opposite direction. And you see this, different molecules produce bands where the head is either on the red side or on the blue side. And in the case of water, the band head, the cliff edge, is here on the red side. So there we go. We're beginning to understand how to recognize the spectra of molecules. I just want to say a quick word about molecular spectra, because the origin of molecular spectra is the same as atomic. It originates with an electron transition, but the complexity and the reason why we get a whole mass of lines that produce a band is that a molecule can also vibrate. So that splits the single electron transition into multiple vibration levels. And that's the origin. For example, there are 3 levels. You could imagine those are 3 of the Swan bands. And then those individual bands split into much finer lines due to rotation, which requires even less energy to trigger. So the band, each band is this broad emission or absorption feature due to the fine structure of rotation. So that's basically how a molecule produces these multiple bands in a spectrum. Now, if you know chemists, if a chemist sees a flame, they like to sprinkle something into it. And I happen to have some barium nitrate to hand, as chemists would. So without my wife looking, I sprinkled some into the flame. And I expected to see this, which is the atomic spectrum of barium. Actually, what I saw was this, which is the molecular spectrum of barium oxide. Now, if I'd done the intelligent thing and done a literature search, I would have found this paper already that basically said this is what you should expect when you sprinkle barium salts into a flame in the presence of oxygen. But I show this because, and again, you see this fascinating band structure. Notice the band heads are all on the blue side, so they're opposite to the Swan bands, the diatomic carbon bands. They're like water. And there are many, many of them, and some of them overlap. You can see an overlapping band here, but they produce this beautiful complex set of bands, and we're going to see these later as well. So now we're beginning to go on this astronomical front, and this is the spectrum of the sun taken out through my kitchen window. And in fact, I can show this to you live. I have my spectroscope pointing out of my window. And there it is. So that's the live view of the sun's spectrum through my kitchen window. And you can see all of these beautiful Fraunhofer lines. The camera's black and white because that gives the best sensitivity and resolution for spectroscopy. The blue is always here on the left, and the red is always here on the right. And visually, you can begin to recognize that some of these features are quite band-like. And here they are. And we're going to talk about all of those in a minute. So I'll just change back to my presentation. There we go. So you see the sun has an absolutely beautiful spectrum full of atomic absorption lines, but up here, these are the bands that we're interested in. And of course, these are the bands that are present in every spectrum that you take. They're the Earth's atmosphere. And here you see the bands due to oxygen. And again, their band head is on the left. It's on the blue side, but these are absorption bands. Here's water, that's the middle one. And these are known as the telluric bands, telluric meaning of the planet, of the Earth. And just to show you, I've just put the emission spectrum of water from that flame spectrum I just showed you. And you can see how the band head lines up with the band head from water, which shows you that we're seeing water in both emission in the flame and absorption from the Earth's atmosphere. Some of the detail is different because the environment is different. We're talking about a 2000 Kelvin flame from burning gas, but ambient temperature for the Earth's atmosphere. So I think now we're ready to jump out to space, and let's start with planets. If you put your spectroscope on Saturn and arrange the slit so that it crosses the ring and then the planet and then the ring again, so that there's a gap, and I've shown the image from the guide camera here, you actually get 3 spectra, one from the ring at the top, then the planet, then the ring at the bottom. And if I zoom in on this area here, you can see these dark features, these bands, present on the planet's spectrum, and they're not present on the spectrum from the 2 sides of the ring. And then if you plot that graphically, you can see these beautiful deep absorption bands in the red curve, which is the planet, that you don't see from the spectrum of the rings. And just to convince you that I'm not cheating here, there's the spectrum of the moon, and that looks very much like the spectrum from the rings. But here's the spectrum from the planet. And what you're looking at here are the absorption bands of methane. And if you want to see this even more clearly, you just have to turn your spectroscope on Uranus. And this has an absolutely amazing spectrum. The methane absorption from the upper atmosphere of Uranus is so intense that it absolutely fills the spectrum with methane absorption bands. So much so that, particularly at the red end, much of the light is absorbed by the methane, and this gives Uranus its characteristic blue-gray color. So the last thing I'm going to talk about is Earth, and Earth as a transiting exoplanet. What do I mean by that? Well, there's a unique moment in spectroscopy to observe moonlight in total eclipse. So this is the schematic of what we see in a total eclipse. This is pretty much the color of a total eclipse that I'm going to show you, that I saw when the full moon turned from this enormously bright silvery thing to quite a muted, beautiful orange color, and all the stars came out. But if you imagine yourself on the surface of the moon looking back towards the Earth, you see the Earth as if it's an exoplanet. And this is what professional astronomers want to do in the future when the James Webb Telescope is launched into space, and when these enormous telescopes are built like the European Extremely Large Telescope. They'll have the capability to tease out the spectrum of the atmosphere of this exoplanet as it travels through the atmosphere, crossing the face of the star. And there have even been studies of what I'm just going to show you using my spectroscope by professionals to practice on the total eclipse spectrum of the moon. So here I took a photo with my camera as the spectrum arrived. I was quite relaxed by this point, had plenty of time to get to my spectroscope and start taking spectra. And here's the view in my guide camera as the totality of the eclipse began to creep across the surface of the moon. And so you can see quite clearly the slit that the light that goes through to the spectroscope passes through. This is the 23 micron slit. And I placed it over the Tycho crater, which is one of the brightest craters on the moon. And here's a little movie I'm going to show you of all the spectra I took as totality crossed over the slit. So at first you see a spectrum of moonlight that looks fairly normal. All these solar absorption lines are present. And then gradually as the totality crosses the slit, you start to see this huge scoop taken out of the middle, which is the spectrum of ozone, and some other absorption lines as well that you don't normally see when you observe the spectrum of sunlight or moonlight through the atmosphere from the surface in a normal way. I'll just run that movie once again. It really was beautiful to see. And if you've not seen a total lunar eclipse, I think the next one isn't until May 2022. So you'll have to be patient, but it's worth it. And the conditions were perfect for this eclipse. It was 3 a.m. in the morning, absolutely flawlessly clear sky. So what we can do is process that spectrum a bit more, remove the any lines due to absorption lines in the reflected sunlight, and what we're left with is what's called a rectified spectrum. So we've rectified it so that there's no shape to the spectrum anymore. The whole spectrum is normalized to intensity 1, and we've removed all of the solar absorption lines, and now we're left with the pure spectrum of transmitted light through the Earth's atmosphere. And you can pick out the molecules now. You can see these beautiful absorption bands due to ozone, known as the Chapuis bands. You can see some oxygen dimer, and these are oxygen bands that you see also in the spectrum that I showed you before. And here's water, relatively little, so it's quite dry, the upper atmosphere, which is where the light comes through that produces the total lunar eclipse. Well, look, now let's go to the stars. And I must admit, before I did spectroscopy, finding molecules in stars I thought seemed unlikely with the temperature of stars, but actually that's not the case. And Secchi, who did the first stellar classifications, as I said, he actually devoted a class of stars to stars that show molecules in their spectra. He recognized this class as stars that have a spectrum with wide bands, and he listed a few good examples: Alpha Ori, which of course is Betelgeuse, and this is Antares. So these are the sort of red stars, orange stars that we're used to seeing in the sky. So here I took a spectrum of Ras Alghethi, which is Alpha Herculis. So the brightest star in the constellation Hercules is actually a beautiful visual binary. I took a photo of it here. We're looking at the spectrum of the brightest star. And can you see this beautiful sequence of absorption bands in the spectrum? Does that look familiar to you? Well, if I put the spectrum here of the barium oxide, of course, that's an emission spectrum, the barium oxide spectrum. These are bands are in absorption, so they kind of point in different directions. But you can see here, these are the band heads, and when you position the heads, you see they all line up with the absorption spectrum of titanium oxide, but in terms of its nature, very similar to barium oxide. So a beautiful spectrum that Angelo Secchi recognized in his early spectroscopy. And then the next set of spectra were sort of prompted by Callum Potter's recent Observers Challenge on the BAA website, where he talked about red stars and looking at carbon stars. So I went out and took the spectrum of Gamma CVN, Gamma Canis Veneticorum, and it was Secchi who gave this name La Superba to the star because it has a most dramatic spectrum. In fact, here's a quote from the paper he wrote, and here's the drawing he made. And as he said, you see these three what look like emission bands, but that's just because the absorption is so deep. The light that gets through appears to be in emission. And here's my spectrum of this beautiful orange star. And you can see that particularly here at this end, there are obvious band heads. And if we zoom in on that, so I'm just cropping the y-axis so we can just focus in on those three band heads. And then we position underneath it the spectrum of the gas hob flame. Can you see how the emission from the flame beautifully lines up with the absorption in the atmosphere of the star? So you know with certainty that you're looking at the absorption spectrum of diatomic carbon in the atmosphere of the star. You're seeing the swan bands in absorption that you see in the blue graph here in emission in the gas hob flame. And there we are, I've labeled them up. There's also, just to convince you, there's the atomic absorption of sodium, always present in these cool stars. And here's the emission line in a flame. I didn't mention, did I, of course, that sodium isn't normally in natural gas burning, but of course it's when you've spilt cooking salt onto the flame, a very persistent spectrum. So now let's finish with comets. Now, when I wrote this talk, of course, there was going to be a really bright comet. Nick James did the first webinar, didn't he? And he promised us a very bright comet. Of course, it's broken up, as we'll see in a minute, but nevertheless, I thought we'd keep this section in because they are absolutely beautiful things to observe in a spectroscope. And William Huggins was the first to take a photograph of the spectrum of a comet. And this is the blue and near UV end of the comet spectrum he took. And this is this amazing bright comet of 1881. And what he did was he picked out the emission lines from the comet of diatomic carbon. And that's this, not diatomic carbon, of cyanogen. And that's these two emission bands here. Now, his spectrum is high enough resolution to actually resolve the individual rotation lines in the bands here. There's, of course, a funny side story to this. Cyanogen is a very poisonous, fatally poisonous gas. And this was recognized even in Huggins' time in the 1880s. And when Halley's Comet was due to return for a visit in 1910, it revisits us every 75 years, there was much panic around whether, because we passed through the tail of Halley's Comet, it produces a couple of meteor showers, whether when we passed through the tail of the comet, we would dissolve, as it were, enough cyanogen into our atmosphere to be fatal. Fortunately, of course, that's not the case. So here is my spectrum of a comet. This was Comet Lovejoy from early in 2015. And here is the top spectrum. Here is the spectrum of the comet. And what I've done is I've put the spectrum below it of the gas hob flame again. And you can see how these swan bands beautifully line up in the spectra of the two bodies. So with certainty, you know that this beautiful emission spectrum from the comet is due to diatomic carbon. So there's carbon present in the emission, in the coma of comets. And here at the near UV end, here is the incredibly intense emission from cyanogen. And of course, I left it in. Generally, when you do spectroscopy, you remove light pollution from the spectrum, which of course means you can do spectroscopy even under light polluted skies. I left it in just to show you how it lines up perfectly with the sodium emission in the gas hob flame. And then here's some very early work done by Robin Leadbeater, who used a very low resolution grating, 100 line per millimeter grating over the front of his webcam. And here's the field of view he had. And he took a spectrum of a comet. And even at low resolution, you can see these emission bands here. And here he's plotted it graphically and identified the beautiful swan bands here. And there's the cyanogen band as well. And then to finish, here's a really nice spectrum of what is, or what was, a very faint comet, and that's the comet Atlas that we were all hoping would be almost naked eye visible. Well, certainly the press were selling it as such. And then unfortunately it began to break apart, and I thought I'd include as well these absolutely beautiful images of the comet taken by Nick James that show the comet beginning to fragment. But David Boyd was very lucky. He got this spectrum on March the 26th, whilst it was still just about bright enough to take a spectrum. And David has labeled all of the most prominent absorption emission lines, emission bands. And I thought really this would be a good place to stop my talk, because David can maybe comment during the Q&A about the difficulties and how he took this spectrum, and that can lead into a nice discussion, not just about molecules in spectra, but just about spectroscopy in general. And I hope you've enjoyed the talk. Thank you.
Great, thank you very much, Hugh. That's fascinating. For the Q&A, we have on your screens, I think for most people, you'll find if you move your mouse down at the bottom end, there'll be a Q&A button, and you can type questions in there. We also have chat, which we can look at, but it'll be easier for people to type the Q&A and the questions. As well as myself, Robin Leadbeater will be joining, and David Boyd on the Q&A. So Robin, I'm just about to unmute you, just to, so there you go, giving you allowed to talk. And David, I'm just going to do the same on you as well. I also happen to notice we have Francois Cochard in the audience of Cheliac.
Ah, great.
as well as John Paraskiva. And I think there's probably a few others who I've missed without going down the full list, because we've had about 130 people on Zoom, as well as 30 to 40 on YouTube. So I think just shy of 170 today. But there might be one or two. If we have any questions which are relevant to them, we may be able to pass them on as well.
Mm.
So just looking through the questions, I see the first one we've got is, what is the slowest F ratio in a telescope that would work for spectroscopy? And that's from Owen.
Yeah, I mean that's a good question, and it depends to some extent on the spectroscope you're using. So for the Alpi, for example, they recommend the slowest should be F10 probably, because then you're not wasting any light because of the focal ratio of the optics in the Alpi spectroscope itself. If you're using a star analyzer, then to some extent, because there's no slit, the resolution, the quality, the sharpness of your spectrum is determined to a large extent by the size of your star image. That, if you like, is the size of your slit. And a slower F ratio can sometimes produce a larger star image. So it can be useful to step the focal ratio down. I don't know if you've got a comment on that, Robin.
Hi, can you hear me okay?
Yeah.
Okay, yeah, with the star analyzer, the more parallel the light is at the grating, the better the resolution. So
Yeah.
that favors slow optics.
A slow ratio, yeah.
On the other hand, the resolution of the spectrum depends on the size of the star.
Yeah.
So as you get slow optics with the same aperture, you end up with big stars. So it's a bit of a compromise. In general, as long as you stay above about F5, then the size of the star image wins, and you're better off using faster optics down to that sort of level. Incidentally, the Alpi, you can work actually down to F4. The optics will work down to F4, so you can use that with fast telescopes. The LIRES, the high resolution instrument, because it doesn't have as fancy, well corrected optics, you have to use it at F10.
Yeah. I mean, light is at a premium, isn't it, when you do spectroscopy? Because when I give talks, I often liken it to sort of spreading a blob of butter. When you capture the light in your telescope, you need to get as much of it onto the diffraction grating and onto your camera as possible, because every photon counts. I mean, thinking of your spectrum there, David, your beautiful spectrum of Atlas, I think that was probably a big challenge for you, wasn't it, to get enough light into your spectroscope?
Yes. Can you hear me okay?
Yes.
Oh, good. Nice talk, Hugh. Thanks.
Okay, thank you.
Well, taking a spectrum of a comet presents a number of challenges. One is the annoying fact that comets move. Most stars that I take spectra of tend to stay in the same place. With a comet, it's moving all the time. And when you're taking a spectrum, typically a spectrograph will have two cameras on it, one which is recording the spectrum, but the other is recording a reflected image from the mirror that you mentioned earlier, which contains a slit in it. That reflected image allows you to keep the object you're observing in the slit. And by feeding back to the telescope mount, it tries to maintain that. Now, with a comet, which is moving all the time, you're fighting that continual motion of the comet, and that caused me some grief when I was taking the first the first spectra of that comet. It took me 3 attempts to get it, partly because it's very faint. Like Hugh said, the light gets spread out. Comet is a pretty diffuse object at the best of times. So the light was spread out. The comet was moving. It took a deep guiding images to actually hold the comet in the slit. And then you find that the image you're getting on the imaging camera, the spectrum is very faint as well. So you need long exposures. Eventually, I ended up exposing for, I think it was about 15 minutes at a time per image, in order to get a bright enough image that I could actually combine together. I was using the software ISIS that you mentioned to put that spectrum together. So it's a challenge, but it's fun to do it, and it's satisfying when you get it at the end, and you can see all that chemistry that going on in this star and this comet as it's approaching the sun, and these molecules like ammonia in the atmosphere are being dissociated by solar radiation to give you the NH2 lines, and similarly with the other elements, the other molecules you see in the spectrum of the comet.
Yeah.
I see we've got 12 questions in the pipeline, so we'll see how we get on with answering those.
Yeah, I mean, I was going to say, Andy, if you do high resolution spectroscopy, so you have the same kind of challenge, don't you? Because in high resolution, you have to spread the light out as much as possible in order to resolve the gaps between the tiny gaps between the absorption or emission lines. But so I think you must be used as well to.
I mean, basically, when you go from low resolution to high resolution, you have to go for brighter targets. You spread the light out more, so the light is spread across the chip and becomes fainter. So typically, you might be looking at a faint target, 6th to 8th magnitude. Occasionally, you can go a bit fainter if you've got something with emission lines, but it is a different when you've got low resolution, because the light's more concentrated, you can go fainter.
Yeah.
If it's okay, I'll move on to, there was a question during the presentation, actually we're now to 15 questions, which was from Peter Williams, and I think this was on your spectrum of the flame. The continuum peaks in the UV, which is surprising, as it's just a very high temperature of around 8,000 K, or is it not a black body?
Yes, indeed. And the right answer is not a black body, because, of course, the continuum in the flame spectrum is actually only an apparent continuum at the resolution of my spectroscope. If you use very high resolution spectroscopy, you actually can see that the continuum is a smeared out band. In fact, it's produced by carbon dioxide. That's the origin of what looks like the continuum. The temperature of the flame is actually only about 2000 Kelvin. So yes, a black body at 2000 Kelvin would actually produce a spectrum that peaks in the infrared. So yes, it's not it's not a black body spectrum. It's actually an emission spectrum disguised. But I thought I wouldn't go into that. But good question anyway. Good question.
I think this one will definitely be from Hugh. It's from Jeremy. What's the highest molecular weight organic molecule you've detected?
Well, the funny thing is, Jeremy, as you probably know, the best wavelengths to detect molecules is in the infrared, and especially high molecular weight ones. And that's, of course, why, for example, the James Webb telescope is an infrared telescope, because it will be perfectly suited to looking for molecules in the atmospheres of exoplanets. But in the visible region, which is where I observe from the surface of the Earth, I would say that the oxygen probably, with a molecular weight of 32. So yeah, you're typically looking at small molecules with sort of visible wavelengths. Actually, ozone, 3 oxygens.
Here's one from Jim Slight. Great talk. How important are flats and controlled light source for calibration?
Yeah, I mean, flats are important for getting the highest quality spectra. And of course, as I mentioned, the ALPI in its calibration module has a tungsten lamp built in for you to take flats. I don't know. It maybe isn't essential. I mean, Robin, do you have a comment on that? The importance of flats. And of course, it's difficult without a slit to apply flats.
Yeah. Flats is a contentious subject. I say yes, you should use flats, and the main reason I like using flats is that it replaces all the vagaries of the variation in the sensitivity of the camera with all its humps and bumps. It replaces that with a nice smooth spectrum from a halogen lamp. And that means it's much easier to do a good instrument response correction and get a nice accurate spectrum. That's the main use I see of flats. What people tend to think is that they introduce noise. And my answer is, if you're introducing noise, you need to take more flats and average them. Flats with a halogen lamp, particularly on the Alpi, only take a few seconds per frame. So if you run it for 10 minutes, you'll get more than enough flats average to get rid of the noise. And it's something you can do easily. So why not do it?
Absolutely. When I use the Alpi, I typically take 30 flats of 11 seconds each. So it doesn't take long, like you say. And there was another part to that question, wasn't there? The importance of a calibration lamp. I mean, it's not essential because, of course, you can use another star with prominent hydrogen absorption lines to calibrate your spectrum. In fact, typically you're always taking a reference star in order to correct for the absorption of light by the Earth's atmosphere. But you can also use that reference star to calibrate your target spectrum. But it is easier if you can to use a calibration lamp. And again, as I mentioned, the Alpi has a module, the calibration module, with an argon neon lamp in it, which gives emission lines all the way down to the near UV and right the way up to the near infrared. So you get good, accurate calibration across the whole wavelength range that you can capture with the Alpi.
One other point on flat lamps. Although it's nice to have them built in like the Alpi, the flats are nowhere near as critical as they are in astrophotography, where you have to have a nice uniform field. You can do a good spectroscopic flat just by waving a handheld halogen lamp in front of the telescope aperture with a piece of paper over the aperture just to even it out a bit. But because it's only looking at the light coming through the slit, it doesn't have to be uniform across the field at all. It's very simple to do.
Another reason that using a calibration lamp can be better than taking a star, using the spectral lines in a star, is that, of course, stars move. You can have stars with radial velocities either to or from us, which can shift the spectral lines by several angstroms. So if you use a star like that to calibrate your spectrum, your calibration would be off. So using a calibration lamp is generally the preferred way of doing it. Certainly the way professionals do it. And I would certainly encourage amateur spectroscopists to use a calibration lamp. Usually one comes with the commercial spectrograph, so it's worth paying the extra money to get it because it gives you more reliable wavelength calibration, which is one of the important factors. If you're trying to produce a spectrum which you want to put in a library that hopefully might one day be pulled down by a professional astronomer who's interested in that object, one of the things they'll want to know is that you've properly calibrated the wavelength of that spectrum. Another aspect that you get involved with is trying to correct for the absorption in the Earth's atmosphere. Starlight coming through the Earth's atmosphere suffers absorption due to the atmosphere. That distorts the spectrum that we actually record. And so a common way of correcting for that is you will take a spectrum of a star whose spectrum you know, and you'll take the ratio between what you actually record and what you know is the spectrum of the star and use that to correct the spectrum of your unknown target spectrum. And that will produce, as I did with that comet spectrum, I used a nearby star to the comet to take out the Earth's atmospheric effect and produce that spectrum, which is more truly representative of the light actually emitted by the comet.
The next question I might field myself to start with and then pass to others for comment, which is from an anonymous attendee. And this is, can spectroscopy be used to find example exoplanets with water? The answer to that is sort of, but you need a very large professional telescope. And I'm not sure it's been done yet because you have the problem of water in the Earth's atmosphere. Basically, a bit like Hugh was showing with the moon, what you do with exoplanets is the star is what you're going to see mostly from the light, and that's the spectrum you'll see. But when the exoplanet passes in front of the star, you'll see the light passing through just the thin edge of the planetary atmosphere. Or when the planet's about to pass behind the star, you'll see reflected starlight from the star. So it's a tiny effect which you have to subtract off. I know there's been a number of detections of some molecules, but it's a very, very crude detection at this time. I think the James Webb is particularly going to be useful for looking at spectra of exoplanets.
And of course, Andy, there is an opportunity to look at the Earth as an exoplanet in reflected light, and that's the spectrum of Earthshine when you see an early crescent moon. I haven't done it myself yet. I'd like to do it and take a look at the spectrum of reflected light from the Earth's surface.
The next two questions are almost the same, so I'm going to read them out together. And then, so from David Galvin, have the new LED streetlights made it difficult to use the basic Star Analyzer 100-200 spectral grating? And from Jeremy, how has the change to LED lighting affected your spectroscopy and your observing generally?
Well, I would say for a slit spectroscope like the ALPI, LED light changes from sodium to LED light probably isn't significant. Not sure about the Star Analyzer, whether it makes the Star Analyzer more difficult to correct for the background. What do you think, Robin?
Well, no, with the Star Analyzer, if you're just using it without a slit, then the sky background, where whatever wavelength it is a problem because it exists everywhere, and therefore it's just a background mush. So that doesn't make any difference. With a slit spectrograph, yes, you have the advantage that it's most of the light pollution is kept out by the slit effectively. But I've noticed when going to very faint objects, looking for my faint supernovae, that the change from sodium, particularly low pressure sodium, over to LED has been quite detrimental for me, because I now get a very mushy band in the blue where there's generally not a lot of signal anyway, and I'm struggling with sensitivity. And subtracting that away, it starts producing a noisy spectrum. So I've seen round here the change from low pressure sodium to high pressure to metal halide to LED, and each step's made life more difficult. I think it's true to say with unless you're going after the very faint objects, the sort of magnitude 16, 17, and even 18 now, you can get away with a lot of light pollution. And if you look at Christian Bouille's website, for example, he does some really ridiculously amazing spectroscopy from his apartment balcony overlooking some horrendous light pollution. So in general, it's light pollution isn't a problem unless you're really pushing things.
And that's, Robin, that's exactly what I say when I give talks about spectroscopy. I like to explain to astrophotographers in particular that really, generally speaking, you can work in heavily light polluted skies in a way that you can't do astrophotography.
Next, we have a question from Terry, which is, can you measure planet rotation with a spectroscope?
The answer is yes, you can. I've seen people do it with, for example, the rotation of Jupiter. You can see the Doppler shift difference between one side of the planet and the other. The resolution of my spectroscope isn't really enough to see that difference in Doppler shift, but I know that people have done it. I mean, David, is the LISA that you have, is that almost enough? Yeah.
Oh yes, I've managed to detect the rotation of Jupiter by putting the slit across the center of the star, and you pick up the differential movement of the two ends of the edges of the equator of the star. I think we could almost see it on that slide you showed earlier of Saturn, actually.
Okay.
You can go back to that slide.
Yeah.
We have the chimes bringing us in for 8 o'clock.
Yeah, apologies for that. Apologies for that.
Everyone can calibrate the video now when they watch it later.
I'll just go to another question, Andy, whilst I just move the presentation back to Saturn, if you like. You're muted, Andy. Andy?
Sorry, had muted. The next question is from Colin Hargis. or Hargis, excuse me if I have that wrong, and it's why do astronomers use wavelength when frequency gives the best link into the physics and quantum theory?
Gosh, good question. Traditional in the subject. Most spectra are presented with, of optical spectra, are presented with a wavelength in angstroms typically.
Yes.
But
I mean,
if you go into radio astronomy, then it's different.
Exactly. Very long wavelengths, it's normal to talk about frequency. So, yeah, I mean, they are, you know, essentially expressing the same thing. But certainly, yes, in optical spectroscopy like we're doing, it is traditional to use wavelength and traditional to use the unit of angstrom.
Or nanometers.
Yeah, people use nanometers. Yeah, absolutely. But it just avoids decimal points.
Yeah. So did you find that?
Yeah, I'm just...
it was there. We went past it.
Did I go past it? Sorry, yeah, I was thinking about answering that question.
Or shall I
yes, carry on, Andy.
Yeah. Be one for, say, Robin was due.
Yeah.
And, this is again from Owen. So would F9 with an ALPI work?
Hi, Owen. Yes, yeah, F9 with an ALPI would certainly work. You would get all the light, you would fit all the light onto the optics. The only limitation is, depending on the seeing and the aperture of your telescope, you might find that the star image is bigger than the slit, and then therefore you start losing light. Not all of it goes through the slit. But F9 with a small aperture and average seeing, say an aperture of, I don't know, 6-inch aperture F9 would work fine, even 8-inch. You'll get a perfect spectrum. The only thing is you might lose a bit of sensitivity if the star image is bigger than the 23 micron slit.
Okay. The point I was going to make is that that gives you a nice example, that spectrum, that if you had slightly higher resolution probably than the ALPI, what you would see is these dark bands crossing the spectrum are actually tilted.
Yeah.
They're at a slight angle.
Yeah.
The one will be slightly, it looks to me like the top one might be ever so slightly blue shifted and the lower one red shifted.
Yeah, careful though here, David, because this is the raw image straight from the camera. So this has not been corrected for slant and tilt and so on.
Okay, but the principle is...
But the principle, absolutely, yeah.
But you can pick up the rotation of planets by looking at the Doppler effect in the spectral line.
Yeah.
Just a quick one. I noticed Susan has her hand up. If you have a question, you can go to the bottom left of the screen and click the Q&A to type a question. The next one is again from Terry, which is, can you see sunspots in a spectroscope?
Ooh. I mean, I have to say I don't know. I mean, I know there are magnetic effects around sunspots that you can pick up as the sort of Zeeman splitting effect in the spectral lines from the sun. But is there somebody who'd know more? Andy, would you know any of the astrophysics around that?
I'm certain you can.
Yeah.
Because I think, for example, with the sun, spectrohelia.
Yes.
Graphs.
Spectroheliograms, don't you?
Yeah, and you can actually see them as well in stellar spectra. So I'm doing a PhD at Exeter, and part of that is to look at star spots on other stars. And what it is, you see in that case, you have two different temperatures. You have the temperature of the stellar surface, and then the temperature of the star spot can be, say, a couple of thousand degrees cooler, and you have two different spectra superimposed. But I know for the sun, I think spectroheliographs use, like you were saying, Zeeman spectroscopy, that kind of thing. If anyone else has any.
Yeah, this was something that I was thinking about doing. You can certainly, if you take a slit spectrograph and put it on the sun, apart from the fact that you've got an enormous amount of light and you'll probably damage the internals if you're not careful. You should be able to see the differences in the spectrum across a sunspot. I wanted to do it because you could do it with the old Lyres because it had metal slit. You could do spectroheliography with it effectively, and I have made images in H-alpha, for example, doing it that way. I think with the new model, it has a glass slit, and therefore I'm worried about damaging it. But as I understand it, if you do take a spectrum across a sunspot, the sunspots are so much cooler that you can actually start to see molecules, and it looks like a cool star. So you start to see, I don't know if it's titanium oxide or what, but you start to see molecular bands. And it's something I've wanted to do, but I can't do now because I've converted my LIRIS over to the glass slit.
Next, we have a question from Tim Milton. The late, great Carl Sagan was interested in the concept of panspermia, which inferred that comets could have seeded the early Earth with the building blocks of life, e.g. amino acids. Are you able to detect these molecules in comets via spectroscopy?
The answer is yes, but not. I mean, you touched on the need for professional equipment. You'd need professional equipment, and I mean, for example, these spectra occur in the sort of infrared microwave region of the spectrum, so you need to really be have that capability. So, for example, ALMA, which is the Atacama Large Millimeter Array, is perfectly adapted to search for molecular spectra at these wavelengths, and indeed simple amino acid glycine has been found in the spectra of comets. I mean, the Rosetta mission, for example, the European Space Agency mission that obviously got very close to the comet, was able to detect the spectrum of glycine molecules in the outgassing from the comet. So yes, absolutely, it is possible, but not with amateur equipment, I'm afraid.
Though I think what we're seeing in the CN and the C2, aren't they the debris from more complex molecules?
Absolutely, yeah. They're like the daughter species from more complex molecules, for sure. And you can maybe do some inference as to the nature of the parent molecule, but yeah, it's difficult to know for sure what that parent molecule is.
Some very complex organic molecules with many tens of atoms have been found in interstellar dust.
Yes.
So there is a lot of complex chemistry going on between the stars as well as in comets.
Yeah.
I think there's a list on Wikipedia somewhere of all the molecules that have been found in space. Some of them are hundreds, molecular weights of hundreds. Quite remarkable.
Yes. I'll just do a plug for next year's Winchester weekend, which unfortunately this year was cancelled, but we were going to have a talk by somebody on cosmic chemistry, which will start to tell you all about these complex molecules that people are now finding. So book up for next year's Winchester.
Oh, you sold it to me, David.
We've had a few people who had to leave from timing, but we still have 110 on and 9 questions to go. So I propose we carry on for the time being.
Yeah, keep going.
The next one is from Jack Martin, and he's asking, what magnitude can you see down to with the unaided eye from your location?
Sorry, say the question again, Andy. You just faded at the end.
What magnitude can you see down to with your unaided eye from your location?
Oh, well, hello, Jack. First of all, nice to see you again, as it were. I don't know. I haven't specifically gone out to measure that, but I mean, the sky here in the Mendips isn't bad, so maybe magnitude 4 or 5, something like that. 4 perhaps, with the naked eye. Yeah.
Yeah, that's about what I would find too in South Oxfordshire, where I am. It's a good night you get to 5th magnitude, but often it's less than that.
Yeah.
And then the next one is from Steve Kimmins. I'm guessing most comet spectra are from the bright nucleus. Is it possible for an amateur to take spectra of the various types of tail, maybe even using a background star to take an absorption spectrum?
Interesting thought, Steve, and hello.
Well, you can put the spectrographic slit anywhere in the comet coma or tail and pick up, if it's bright enough, some light from that, whatever is in the slit. So you can study different aspects of it. And it's interesting, if you look at the spectrum of a comet, depending on where you integrate and draw your spectral profile, you see significant changes in the relative contribution of different species to the spectrum you see. So there's a lot of variation across the coma of a comet.
Yeah, I think, as you touched on, David, I think the challenge in the tail would be getting enough light.
That's right.
And therefore getting a spectrum that sort of sticks above the noise.
Next time we get a Hale-Bopp.
Yeah, exactly. That's what we need. We need a fantastic naked eye comet.
Yeah, I've seen some comet tail spectra by Paolo Berardi. I can't remember which comet it was, obviously a bright one, but he put the slit in various places across the tails and could pick up as you go out, you get less dust and more gas if you go through the coma effectively. Also, I've seen a nice star analyzer spectrum taken of a comet which had a lot of sodium in the tail. And the star analyzer, the image is effectively the image of the comet in sodium. So, you know, with the star analyzer spectrum, you get a series of images at each of the emission lines effectively. And it produced a nice orange sodium comet tail.
That's very nice. Yeah.
The next one is from Kelly, UOR. I'm not sure if that's University of Reading or somewhere like that. I might field this one to begin with and pass it on to Hugh, but it's how many spectra of known elements and molecules are yet to be mapped? Can amateurs help in this field? And where do you see the future of spectra going? Is it possible to use spectra in the quantum world, for example? In astronomy, I know that for stellar spectroscopy, there's a mix of sort of professional spectral line libraries which are used, which some of them are based on computer modeling of quantum mechanics and some from actual observations in the lab. And those typically have millions, tens of millions of spectral lines in them for the molecules. And then those are used in sort of modeling spectra and from stellar atmospheres, which can then be compared with reality. Hugh, in his chemistry background, probably knows similar along those lines.
Yeah, I mean, one answer I would give is that I went to the Caroline Herschel lecture at Bath University, just down the road from here. Not the very recent one, but the first one last year. And that was given by a woman involved in the search for biosignatures in the atmospheres of exoplanets. And she explained one of the difficulties for this emerging field is having sufficient reference spectra. You know, there are many sort of complex molecules or complex environments that where the spectra that we could anticipate have never been mapped, have never been reproduced in the laboratory or even with mathematical models. And she said this was quite a big gap in the field, and that needed plugging, if you like, before these big telescopes come online and start producing spectra that no one can decode. So yeah, it's definitely an interesting question, an interesting field.
One of the early problems in spectroscopy was the appearance of lines that people didn't recognize, and they became known as the forbidden lines because they only are formed under conditions of near vacuum. Which are difficult to obtain in laboratory on Earth, but is very common in space. So there are strange conditions in some cases that you observe spectroscopically that we don't see normally on the Earth.
The next question we have is from Steve, and this is more of a practical one about the Velcro bulb. And just for attendees who may not know, basically these are bulbs which emit a spectrum with sort of emission line spectrum, so you can use for calibrating your spectrograph. And Steve is asking about whether you've seen anomalies where the hydrogen has leaked out and disappeared from the Velcro bulb. He's seen that in his homemade calibration module.
Yeah,
oh yes, that's certainly been observed in some of the calibration lamps with the Shellyak spectrographs that they have started off with a hydrogen line, hydrogen alpha line there that has gradually disappeared.
But it's And hydrogen, it doesn't really matter because the hydrogen lines are so broad that they're not very good for calibration anyway. So they're best avoided for calibration lines anyway. But yeah, I have an old one. I have an old Relco lamp which has no hydrogen in it now, as far as I can see.
I think they were mainly a source of confusion to people because it was a line that wasn't in the list of lines, and people were wondering what it was, and that's turned out to be hydrogen.
It's much more fuzzy though than the other lines.
Yeah.
Now we've got Peter Williams asking, what sort of continuum source temperature accuracy do you need to get the radio matrix response accuracy?
Well, I don't think you don't calibrate that way. You don't use a black body for calibration. You use a known star, which is traced back by professionals to radiometric standards. So we're using substandards effectively to calibrate for flux.
And I was just trying to, he's got a follow-up question. I was just trying to work out whether that was related to the last one, but it's relative response of the detector. So
what's the question?
I'm not entirely sure. I think we've probably answered it, I think, in the replies. If not, Peter, do you want to re-ask it, and we'll, if we have time, we'll come back to it. Next again is Colin Hargis. What is the reason for the cliff edge in the molecular spectrum?
Good question. And the fact that the cliff edge appears on the blue side or on the red side, depending on the particular molecule. I mean, it is a very complex subject, the spectroscopy of molecules, but essentially each band is a forest of rotational emission lines. So each band is a vibrational transition to reach that level of energy, and then that transition splits into this forest of rotation lines. So I guess the cliff edge, one side or the other, is where these lines begin to naturally bunch up, and it occurs either at the short wavelength side or at the long wavelength side. But you see these rotational transitions begin to sort of bunch up together, one side or the other. So it's probably not a complete answer to your question, but it is very complex, the field of molecular spectroscopy.
Yeah, I would guess it would be some kind of quantum energy level.
Yes.
These sort of rotations, thinking of the analogy in kind of just a simple atom, where you kind of jump to another energy level, or you just get closer and closer to a kind of where it makes very little difference if you have any sort of add any more energy in there. The next one is from Jay Ribeiro. In high resolution spectra, I use tellurics for wavelength calibration. So,
well, I don't do the very high resolution spectroscopy. I mean, you do, Andy, for instance. I mean, I know there are these very fine water lines, for example, around the hydrogen alpha line that you can use to calibrate. I think that's right, isn't it?
Yes. Yeah. So not sure if anyone else wanted to grab that.
Is that Jose Ribeiro? Hi. So you can use tellurics at high resolution spectra, where in the parts of the wavelength of the spectrum where there are tellurics. So there are a lot of really useful ones around hydrogen alpha. But generally, if you're working other places in the spectrum, there aren't any tellurics. Also, if you're in a nice high altitude observatory or in a desert, then the tellurics can be very faint. But the tellurics are used, for example, to check calibration of people's hydrogen alpha spectra before they go into the BE star database, for example.
I think we're also encouraged not to remove the tellurics from our spectra when we post them in databases, because they provide an independent way of somebody reading the spectrum, double checking your wavelength calibration.
we've got 3 questions left, so I suggest we try and get this all done in the next 5 to 10 minutes. So the next one is from NL. Absolute astrophysics noob here, so this might be a stupid question, but are there any interesting, unique features in the spectrum of a pulsar? And how professional has your equipment to be to acquire one?
Wow.
A very big aperture.
Yes, I mean they don't produce a lot of light. I don't think, not the sort of wavelengths that we could observe. They're essentially.
This is another one on my bucket list, actually.
Is it really?
Yeah. The pulsar, the Crab pulsar, for example, is magnitude 16, so that's within my reach. So I could certainly take it. I think the problem is, I believe the spectra of neutron stars are extremely boring and don't have any features in them.
I think the trick here is the fact that they're mostly neutrons, and therefore there isn't much interesting going on to generate some nice spectral features. Essentially, you've probably got a sort of some kind of broad continuum. Would that be right, Robin?
I believe so, though neutron stars aren't all neutrons. They have this thin skin over them, I think, which can form lines. But the ones I've looked at the resolution I would be using to get a magnitude 16, there didn't seem to be anything there, which was a bit disappointing, I must admit.
Next is from Thierry Payet. Which database of spectral lines bands do you use? Are they publicly accessible?
Well, I mean, I've got a very good book by Richard Walker, the Spectral Atlas, that you can use as a really good starting point. You know, he's basically reproduced in that atlas in really beautiful illustrations of the spectra across the whole range of spectral types of stars and other objects as well. And he identifies with the relevant wavelengths, he identifies many of the absorption or emission lines that you're likely to see. So there's an example of a very good resource, Richard Walker's Spectral Atlas.
And also, a lot of the free software comes with little spectral databases,
yes,
like BAS and I think VSpec or. So basically, that helps you to identify the lines, but you do have to be very careful. And using something like Richard Walker's Atlas is good, because just because you find a line at a particular location doesn't mean that that's that particular element or molecule, because it very much depends on the local conditions of temperature and pressure.
Yeah, that's something that you see people do. They just go and look at the line lists and see a line close to where their line in their spectrum is, and they label it up. But in fact, really, unless you're doing very high resolution spectroscopy, or even then, you have to really understand the physics of what's going on and what you'd expect to see out of the multitude of possibles that turn up in the books.
I mean, Robin, in the supernovae spectra that you're doing, the lines are nowhere near where you'd expect them to be, are they?
Yeah, and more than that, they're so broad that
they
blend into each other, so you've no idea what's there.
Yeah, so
we use clever modelling, mathematical modelling to predict what the spectrum should look like if you had these lines at this width and this redshift. So. But it's pretty difficult. What you do actually is you just match the shape to a known supernova. You don't even bother to really identify the lines, at least initially.
Yeah, and the final question from Christian, I think we've actually just covered. It's to do with what spectral catalogues or software is used for spectral line identifications. I noticed that we have hands up by Susan and Jeremy. If I lower your hands, either can you quickly write in the Q&A, or if you raise again. Otherwise, we'll draw things to a close. I'm just going to switch over the screen for a moment.
You want me to stop sharing, Andy?
That's okay. I can.
You can.
Yeah. I can do the master, the deviant control from here.
Yeah.
So, thank you very much, Hugh, for a fascinating talk, and that was
it's a pleasure.
Really good to get into some depth there, and also to Robin Ledbetter and David Boyd for joining in the Q&A to make a nice, fun, interactive session.
Thank you. Thanks to all of you.
Next week, the 7 p.m. BAA Wednesday webinar is part 2 of Dr. John Mason's talk on Sir Patrick Moore, the early life, mentors and notebooks. Dr. John Mason is the trustee and archivist for the Sir Patrick Moore Heritage Trust, and we were treated to a wonderful part 1 about a month ago. So I'm certainly looking forward to this as part 2. And keep your eyes posted on the BAA website, where if we have any other webinars, we'll put them up. But at the moment, the next webinar is going to be a week today at 7 o'clock. Thank you.